right. So today it's a great pleasure to have Professor Clayton Scott give us a talk. So Professor Scott is a professor in our department, and his research focuses on statistical machine learning theory and algorithms with particular emphasis on non-parametric methods for supervised and unsupervised learning. And his research has many applications in computation and scientific domains such as brain imaging, nuclear detection, threat detection, and environmental and biology. And today he will be talking something very interesting on label noise. Ignorance is bliss. So, and his collaborators is also here. Yeah, let's welcome Clayton.
Thank you, Ching. All right, thanks everyone for coming, and thanks to those of you on Zoom. I'll do my best to monitor the chat if there's any questions. So this is joint work with Yi Loon, who's here, and Jin Shin, and Aditya, who was a postdoc here and is still working with us. This is a talk I'm also going to be giving in a few weeks at a workshop to a group of experts in this topic, statistical learning theory and domain adaptation. That's going to be a 40-minute talk, so I've tried to add at least 10 minutes worth of slides and material to explain some of the concepts that I probably won't need to explain to that audience, but I tried not to. I honestly prepared this thinking of that presentation, but I hope I've added enough content to make it more accessible. And if you have any questions, of course, please interrupt me at any time. Okay. Noisy labels. So it's just a sort of a fact of life in modern machine learning that we have noisy labels. Just to motivate this, you can think of ImageNet, which supposedly has accurate labels, and those were obtained using 48,000 human labelers. Each image was labeled at least 3 times by a human, and I guess they took the majority vote. I guess majority is maybe not the right word, but the consensus of the human labelers to label the ImageNet images. And it took 4 years to generate all of those labels. Collecting the unlabeled data was relatively easy, but getting the labels is very labor intensive. And still, there are errors in that labeled data set. So despite all of the effort, you can imagine most people don't want to invest those kinds of resources in labeling their data. They don't have those resources. And so if you have millions of images, what do people do? They typically will use some kind of artificial intelligence to crudely assign labels. So we can just think of those as noisy labels. And there's actually companies whose business it is to help other companies with noisy data clean up their data and improve their deep learning models to overcome this issue. So noisy labels in classification is just a pervasive problem in modern machine learning. So I'm going to talk about it today. Before I'm going to introduce a probabilistic way of thinking about label noise. Before I do that, and to set that up, I just want to first talk about the conventional way of thinking about classification. And for now, I'm going to restrict my attention to binary classification, but everything our contributions will actually be for multi-class, but it's just a little bit easier to talk in terms of binary classification. So the typical setup is we have a feature vector X and a label Y that are jointly distributed. And their joint distribution is characterized by the marginal distribution of X, the feature vector, and the conditional distribution of Y given X, which, because Y is binary, is determined by this conditional probability, which we call eta of X. And I'll call that the class posterior, or just the posterior for short. That's in contrast to the prior, which would just be the marginal probability of Y. Here it's the probability of Y conditioned on X. All right, then the goal in classification is to attain a classifier with a small risk, R of F. And the smallest possible value of the risk is denoted R star, and that's called the Bayes risk. And it's well known the classifier, or a classifier that attains that Bayes risk has this form. It basically predicts according to whether the posterior is greater than or less than a half. And that's called the Bayes classifier. Now, we don't know this joint distribution, so we want to learn it from training data. That's the standard setup in classification. In label noise, we do something analogous, but now there's a jointly distributed triple. So X is, a feature vector. Y is the true label associated to that feature vector, and Y tilde is the observed label. So Y is not observed. X and Y tilde are observed. And so again, this joint distribution is typically characterized by, got the marginal distribution of X, the conditional distribution of Y given X, and then the conditional distribution of Y tilde given Y and X, right? And so these two are the same as in the previous slide. And the addition is what I'll call the transition probabilities. So it's basically, given that the true label is Y, what's the probability that the observed label is corrupted? All right, so we've got, so from this joint distribution, we can extract the marginal distribution of X and Y, and that determines a classification problem. So just like on the previous slide, we've got a risk. I'll call it the clean Bayes risk, thinking of Y as the true label. So there's no noise. R star is the clean Bayes risk, and F star is the clean Bayes classifier, just like in the previous slide. But we also have the marginal distribution of X and Y tilde, which defines another classification problem, which has its own risk, which I'll call R tilde, and Bayes risk R tilde star, and Bayes classifier F tilde star. And so now in label noise, we observed data from this joint distribution of X and Y tilde. And this is what the learner has access to. So with this information, using a standard learning algorithm, we would minimize the noisy risk, but what we'd really like to minimize is the clean risk, right? We still want good performance with respect to the clean risk, right? Because we assume in our test data, our test data are going to be drawn from this distribution, and we want to predict the actual label. We're not interested in predicting the noisy label at test time. We want to predict the actual label. So this is the goal of learning. So there's different models for label noise, usually broken down by in terms of these transition probabilities. So the simplest, this sort of goes from simplest to most complex. The simplest, we just assume that the probability of corruption is just independent of the feature vector and the true label, just some constant rho. A little more generally, you could assume that the probability of corruption depends on the true label, but not on the feature vector. In the third case, the probability of corruption depends on the feature vector, but not the label. And then the fourth case is the most general and the most challenging situation where the probability of a corrupted label depends on both the feature vector and the true label. So there's been a lot of work on all of these problems. As far as theory goes, however, the theory is mostly focused on the first three cases. And, there's probably because this one is quite challenging, as we'll talk about. But this is going to be our focus. And we're interested in both theory and algorithms for solving this type of situation where you've got label noise that's dependent on both the label and the feature. All right, so the outline for today's talk is going to be a theoretical framework that treats this most general setting of label and instance dependence. And we're going to do so by adopting the perspective of domain adaptation. I'll tell you what that is. So it's a novel perspective for thinking about label noise. So this is going to lead to some theory, some algorithms with some theoretical properties, but then we'll also see that it leads to some practical implications. So I'll show some experiments. And then the take-home messages of this talk, the first one you can deduce from the title. It's in the setting that I'll present, just doing standard empirical risk minimization with the noisy labels is very hard to beat, right? And I'll justify that theoretically and experimentally. The other is that the theoretical framework that I'll talk about actually extends to more general types of domain adaptation problems than what I'll focus on today. Okay, so so this workshop I'm going to, it has domain adaptation in the title, so most people there will be familiar with the problem, but for those that aren't, here's the gist of domain adaptation. Basically, you can think of it as classification where your test data comes from a different distribution than your training data, right? So the terminology that's used is you have your source domain. So that's some joint distribution on X and Y. And that's defined in terms of the marginal distribution Px and the posterior A to P. And then you've got a target domain with another joint distribution. So the idea is you have labeled data from the source domain, but your test data is going to come from the target domain. So we'll assume we have labeled data from the source domain, and in domain adaptation, there's different variations. Sometimes you might have some data from the target domain. It may or may not have labels. There's different variations. But people have come up with names for different types of domain adaptation problems depending on how the source and target differ. So one of those is called covariate shift. And in covariate shift, the X marginals differ. Okay, so the posteriors are the same, but the X marginals differ. That's called covariate shift. In prior shift, that means the a priori class probabilities differ. You know, the prevalence of class 1 relative to class 2 changes from source to target. And these first two are both illustrated here at the bottom. Let's say here's your source distribution. So in covariate shift, the X marginal changes. The decision boundary stays the same because the posterior isn't changing. The posterior is what determines the decision boundary, but the X marginal changes. So your data might look like this. In prior shift, the relative proportions of the two classes changes. And so it might look something like this. And in prior shift, the decision boundary may or may not change. It could change, actually, although that's not shown in this figure. There's a third type, which is not illustrated here, called posterior drift, where A to P, where the posterior changes, but the X marginals remain the same. And this is the one that's relevant for label noise, as I'm going to explain. By the way, I didn't include the citation, but someone did a recent empirical study where they looked at dozens of domain adaptation problems. And they were just wondering, you know, of all of these different models, which one occurs most frequently in real data? And the conclusion was that it's posterior drift. So, you know, so covariate shift is very widely studied. There's lots of papers on it. It's been around for a long time. But it's actually relatively uncommon. Prior shift can be quite common, but it's a pretty easy problem because there's just one parameter that's changing in your distribution. And then posterior drift can be quite challenging because your Bayes classifier is changing, but it's actually quite common. All right. Yes.
So why is the decision boundary not changing in the case of covariate shift? Because from your diagram or from the picture, there are more blue points compared to the yellow points, right? In the second figure.
Right.
So I would assume that the decision boundary has a bit to the left.
Yeah, so in covariate shift, it's assumed that A to P equals A to Q. And the Bayes classifier is defined as the sine of A to P minus a half, or the sine of A to Q minus a half. So those two Bayes classifiers are the same in covariate shift.
A to P here is the label noise, right?
Well, I haven't. So here I'm talking about domain adaptation in sort of an abstract sense, but I'll connect it to label noise in a second. Yeah. Yeah, so in covariate shift, the Bayes classifier doesn't change. Okay. So as to view label noise as posterior drift, so I had this probabilistic model that I talked about before, where you had X, Y, and Y tilde that were all jointly distributed. This is basically a different perspective, a different way of framing it probabilistically. So, so imagine a label noise problem where our source is the noisy distribution. That's what we get to observe data from. But our target is the clean distribution. That's where we actually want to measure performance, right? So the source would be PX with the posterior eta tilde. Eta tilde here is the noisy posterior. And the target is characterized by PX and eta. So you'll notice they both have the same X marginal, which means we're in the setting of posterior drift. And in the setting I'm going to be looking at, there's no data available from the target domain. So this is a little bit different than the previous. Oh, I think my notation here may have changed. Sorry. I think previously I was calling this rho k of x. So let me change that notation. But you know, I haven't referenced these transition probabilities. Functionally, that's okay, because you know, I want to do something that's very general and that doesn't make any assumptions about these transition probabilities anyway, and we don't need them to specify the problem, right? So to generate the noisy training data, all we need is px and eta tilde. To generate the test data, all we need is px and eta. We don't need these transition probabilities, functionally speaking, to set up this problem.
Buddy, can you say a little bit more about why posterior drift is this particularly common form of domain adaptation? Because I think the features might change over time or something. So
Yeah. Honestly, I haven't read the paper, so I found it yesterday.
That's important in case you're
Yes.
yes.
Yeah, so that's some homework. I think I did forward it to Yilun, so hopefully Yilun will digest it. And okay. So in essence, for the rest of the talk, you could think of it as, you know, a framework for label noise, but also you could just instead think of it as a framework for learning under posterior drift. So in prior work on posterior drift, people have made different, you know, you still have to make some assumptions. You still have to make some distributional assumptions if you want to prove something, right? If eta and eta tilde can differ arbitrarily, then, you know, it can be hopeless. So people have imposed different assumptions. So in one of my earlier papers, I looked at the case where eta and eta tilde were monotonically equivalent. You know, one is a monotone transformation of the other, and analyzed it looking at a different performance measure than the one I'm looking at today. Today, I'm focused on the 0-1 loss and the associated risk. More recently, some people have looked at the case where basically the clean and noisy Bayes classifiers are the same. So in other words, eta minus a half and eta tilde minus a half have the same sign everywhere. Right, so this is a very restrictive assumption. Right, if here's x, and here's my posterior probability on the vertical scale, right? Maybe, I mean, if, and well, let's see. Let's say there's 1/2. You know, maybe the clean posterior looks like that. And so this assumption is saying that the noisy posterior, it has to cross the line 1/2 at the same point. And it's basically like saying, well, I feel like it's just a very restrictive assumption. It doesn't really match realistic label noise, which may be generated by biased human annotators or by AI algorithms. So there's really not a lot of support for this assumption. There's also recent work that came out of Michigan the stats department. Shubha Mehdi was a PhD student there, advised by Yukai Sun and Muli Banerjee. And they came up with a model where eta and eta tilde were related by a linear adjustment on an appropriate scale. So that would be a parametric model for posterior drift. What I'm interested in is something that's more flexible. I don't want to assume a parametric model. I want to be non-parametric. And I want to allow the noisy and clean Bayes classifiers to differ, because that's just more realistic. And so to do that, it requires a philosophical shift. You have to let go of consistency as your goal. Consistency is this idea that, you know, the clean risk, the clean excess risk gets driven to zero as n goes to infinity. And that's what the prior works are trying to do. So we're going to, you know, this posterior drift is a hard problem. If you want a realistic model, it's going to be really hard to attain that. So we're saying let's let go of that goal. Instead, let's accept an irreducible error. So this excess risk is going to be bounded away from zero. And instead, suppose our goal is just to get as close as we can to that bound. This, again, to mention some related work, there's a paper that takes a very different approach to what I'll present, but has more or less the same philosophic, shifted philosophy here, and leads to some of the same conclusions that I will talk about. But it's just a different setting. We feel it's a less flexible setting. They basically assume that the total amount of noise is bounded in that sense. And they're able to show that under that assumption, the best you can do in a minimax sense is to just be, ignorant of the fact that your labels are noisy. Just naively train your classifier as you normally would, and that turns out to have I won't say achieve, but it scales with the bound, the lower bound that they can show. All right. So we want to come up with a distributional assumption for posterior drift that's very flexible. Well, let's look to standard classification for some inspiration. What kinds of non-parametric assumptions are used in standard classification? So the quantity, the absolute value eta of x minus a half, is viewed as a measure of signal strength. In other words, the larger that quantity, the more confident your Bayes classifier will be about its prediction. Right? If eta of x is 1/2, you have no confidence in your prediction. If it's 1 or 0, you have maximum confidence. And so that's reflected in some common assumptions that people use to prove performance guarantees in standard classification. There's one called Massar's noise condition, and it says that the posterior is basically bounded away from a half. Okay, so the posterior doesn't get arbitrarily close to 1/2. This is a very strong assumption. A more relaxed assumption is Sivyakov's noise condition, which says that the probability that eta of x is within t of a half decays as t goes to 0. right? So say just saying, okay, the posteriors can, they can cross the 1/2 line, but they don't spend it doesn't spend a lot of time there, or time isn't the right word. It's not there with high probability. Anyway, these are common assumptions in the literature. And so we were motivated by these, and we were wondering, can we do something analogous in a label noise setting? What would be an analogous type of assumption in a label noise setting? And so to begin to answer that, the first thing you have to do is ask yourself, well, what's the appropriate notion of signal strength in this posterior drift setting? So we introduced something called relative signal strength. All right, so given a triple, this is basically a posterior drift problem defined by px, eta, and eta tilde. So we define the relative signal strength at x in a case-wise manner. So in the first case is when the noisy and Bayes, so I keep saying that, the noisy and clean Bayes classifiers agree. And the second case is when they do not. So if they don't agree, we say the relative signal strength is 0. In other words, solving the noisy problem doesn't help you at all. Doesn't help you solve the clean problem at all at a point X. It's sort of a point-wise notion. It gives you basically the wrong information. So there's no useful signal there. But if they do have the same sign, then we define the relative signal strength to be this ratio, where each of these is the signal strength from conventional classification. So when is the relative signal strength large? It would be in a setting where maybe the clean Bayes classifier has a low confidence for a given X, but the noisy Bayes classifier actually has a higher confidence. So that'd be a very advantageous setting. It's maybe unlikely, but that'd be an advantageous setting. So call that high relative signal strength. So then that motivates a Massar-like condition. Let kappa be a non-negative real number, and we're going to define a set A kappa. Basically, the set of all points in our input space where the relative signal strength is greater than kappa. So, in Massar's condition, we assumed the signal strength was greater than some constant. Here we're assuming the relative signal strength is greater than some constant. So if kappa is 0, this is just the set of all points where the clean and noisy Bayes classifiers agree. If k is positive, it's the set of all x where this ratio is greater than kappa. Let's try to visualize this. Here, the red curve is the noisy posterior, and what is this, purple? Blue? The blue curve is the clean posterior. Okay, so here's just a hypothetical situation. Suppose this is our posterior drift problem. Okay, so here's the line 1/2, which determines the Bayes classifier. So this shaded region So this horizontal axis is like that's my input domain. The shaded region is where the two Bayes classifiers differ. The noisy and the clean Bayes classifiers differ. Everywhere else they agree. And so this on the right plots the relative signal strength. So in this region where the Bayes classifiers disagree, the relative signal strength is 0. Otherwise, it's positive. And it depends on this ratio. Okay. And then the set. So this would be. Yeah, so A0 is the set where the noisy and clean Bayes classifiers agree. So this would be the complement of that set. And then this shaded, what color is this? I don't know. Just red? Okay, good. And what is this? I'm colorblind in case you didn't know. Orange? Okay, I said red, didn't I? You knew what I meant. Good to know. So this red region is A sub 0.4. So it's basically everywhere the relative signal strength is at least or is greater than 0.4, just as an example. All right. You can formulate this all in a multi-class setting. I've been focused on binary just because it's a little bit easier to present. But in the multi-class setting, I don't even want to go through the details of this slide, but suffice it to say, there's nothing too challenging about it. It all works out just fine. So let me not even bother with going through this notation, but it has the same interpretations. And so this is so now we're going to define a posterior drift class. In other words, a set of posterior drift problems in terms of this Massar-like condition. So epsilon is a probability, kappa is greater than 0. Actually greater than or equal to 0. I think that it should be. And so we define pi of epsilon kappa to be the set of all posterior drift problems where px of a kappa is at least 1 minus epsilon. So in other words, the set of X where the relative signal strength is greater than kappa has probability at least 1 minus epsilon. Okay. So it's a very general set, you can obviously you can vary epsilon and kappa to encompass just a broad range of different problems. The larger kappa is for a given epsilon, the easier the problem should be because your relative signal strength is larger, right? So this is a class of distributions, and so we can ask a natural question, what is the minimax risk for learning or domain adaptation or learning from label noise over this class of distributions? All right. So we have a couple of theorems that I'll present. The first is a lower bound on the minimax risk. So here, Zn is just shorthand for all of the training data. This is the training data you get with noisy labels. Or, in a domain adaptation settings, your data from your source domain. Here you've got, here F hat indicates a learning algorithm, just an algorithm that, is based on that training data. And this is your excess risk. So this is minimax. You're only looking at distributions in this particular class we just defined. And this is bounded below by an expression with two terms. And the key point is the first term doesn't depend on n. Right? This is just a positive constant, right? I guess assuming epsilon is greater than 0. So in other words, this excess risk can never be driven to 0, which makes sense. If you think about it, there's this, with probability at least epsilon, your noisy and clean Bayes classifiers disagree. How can you learn at all? How can you learn anything on that set without additional knowledge? And then a second term, which does go to 0, and this comes from the part of your input space where the noisy and clean Bayes classifiers do agree. And this is just a conventional rate for supervised learning. Right, so that's a lower bound. And so this is what I would refer to earlier as an irreducible term, right? It's not going to 0. This is not typically what you see. Typically in, theoretical machine learning, theoretical statistics, the right-hand side, it goes to 0 as a function of n. That, that means you're because the goal is usually to show consistency with some rate of convergence. We also have a somewhat matching upper bound. So let me emphasize this is one possible upper bound. One possible theoretical model. There's actually a lot of, we haven't done it, but I feel like, there's a lot of different versions of this theorem that could be stated with different rates and different constants. This is just, a very, very basic one. Or I should say it's analogous to a very well-known result, very classic result in the theory of supervised learning. So again, suppose you have a posterior drift problem in this class pi epsilon kappa, and consider a function class f with a finite Nadarajan dimension v. What is Nadarajan dimension, you say? Well, it is the multi-class analog of VC dimension. Now, you may say, what is VC dimension? I don't have time to explain that, but VC dimension is a classic notion of complexity in statistical learning theory. So it basically says that the functions, the classifiers in the set F can't be arbitrarily complicated. So in a certain sense.
Just a remarkable
Yes.
VC dimension thing. It's basically measuring the learnability of the problem, right? In your hypothesis space.
Yes. Yes. Finite VC dimension characterizes learnability. That's right. Right. And I think the same is true for Natarajan dimension. So in that setting, if the noisy Bayes classifier belongs to this set F with finite Natarajan dimension, and you just do good old empirical risk minimization on your noisy training data, that excess risk has this upper bound, which first let me comment. If you adopt this assumption of finite Natarajan dimension, the lower bound I just showed doesn't change. And so you can compare that bound to this one. And the only real difference is that in the lower bound, we had a factor of 1 minus 1 over k right here. So there's a little gap between our upper and lower bounds.
You said that
Yeah.
the only factor, but there was no v in the lower bound.
As far as so in the irreducible term, you're right. Yeah, the lower bound didn't have a kappa, or did it have a kappa actually? Yeah, there is a kappa. Oh, okay. So I didn't give you the most precise statement. Maybe I should do that, but or just omit v from this version. I don't know, but
Was v on order of 1, or is v like?
v is just a constant, so it gets absorbed.
So it could go in the big O.
It could go in the big O, yeah. But if you prove the lower bound and you also assume the noisy Bayes classifier lives in this class with finite Noetherajan dimension, you can also get the v explicitly in the lower bound if you want to.
I see. Okay. Okay.
It's so okay. Maybe I'll think of ways to represent this. Yeah. All right. So the takeaway messages: noise ignorant ERM does pretty well. And furthermore, it's a very simple algorithm, right? At least conceptually. I haven't talked about implementation, right? It's the 0-1 loss, so maybe implementation is challenging. But actually, that's not a big issue either. We have surrogate losses that can make it computationally feasible. Furthermore, the algorithm doesn't require knowledge of epsilon or kappa. So in that sense, it's adaptive. So whatever your posterior drift problem is, it should live in this set pi for some choice of epsilon and kappa. And whatever that is, this algorithm will adapt. It doesn't need to know epsilon and kappa, and it will still give you a performance guarantee. Now I focused on this Massar-like condition. There's also a Sibikov style condition that we've developed. I'm just going to skip that in the interest of time. But you can ask me about it afterwards if you're curious. Okay, so now let's switch in the last 10 minutes to the some practical aspects of this theory. So if you have followed the developments in deep learning, there's this, it's well known that if you take a deep learning architecture and you have noisy labels and you train it conventionally on those noisy labels, the performance on clean test data degrades as the amount of label noise corruption increases. Right, so that's a phenomenon that's been called tempered overfitting. So you may wonder, how do we reconcile that with the message that I gave previously, which says noise ignorant ERM is good, right? So the way we've reconciled that is, well, it's not really at odds with our theory. The problem is that for a deep network, the Noetherajan dimension is just going to be ginormous. So you wouldn't expect good performance anyway based on that theory. So it's really not applicable. It's, you know, if you're in an over parameterized regime, those bounds can never be less than 1. So it's not meaningful. So a simple alternative is to use noise ignorant ERM to fit a linear model on pre-trained features. This is sometimes called linear probing. Although if you search on linear probing, you get something in like, it has to do with hash tables. It has nothing to do with machine learning, but anyway. Some people call it linear probing. Just fix a pre-trained feature extractor and then fit a linear model on top of that. In a noise ignorant way. So that's what we did. That's what Yilun tried out. And it worked remarkably well. And we were a little surprised no one had done this before in retrospect. This is a synthetic data experiment where we took the CIFAR-N image database, which has 10 classes, and we injected our own label noise. And in this case, it was symmetric label noise. Basically, the true label gets corrupted to one of the other labels with equal probability, and where the probability of corruption is this x-axis. And so we compared several models. One is just a linear model, like no deep learning at all, just a linear classifier. And it does quite poorly, like it never gets above the little legend here. You've got ResNet 50, which exhibits this tempered overfitting phenomenon. So this is, you know, like training the full ResNet 50 architecture from scratch on noisy labels. And it degrades as you get more label noise. That's a previously observed phenomenon. But then we looked at this proposal of pre-trained features and just fitting a linear model. And then we just use logistic regression to fit the linear model. And we looked at a couple of different pre-trained feature extractors. One was one that Yilun cooked up using a contrastive loss to train ResNet 50. That's a technique for what's called self-supervised learning. It's a way of training a feature extractor without knowledge of any labels. And there was another one that's called, I don't know if people say Dino or Dino, but this is published last year. It's a really good feature extractor that other people have developed. You could call this a foundation model. It's basically a foundation model for images. It's trained using just a large number of different image databases in a self-supervised manner. And it gives the best performance. And it gives,
what's its feature dimension?
What's the feature dimension in Dino?
It's about 1,000.
Around 1,000? Okay, thanks, Yilun. By the way, this dashed line is the theoretical limit beyond which you can't hope to learn, right? If more than 90%, if the probability of flipping the label is more than 90%, then the majority, when you're to the left of this line, the majority label is going to be the true label. And so you can hope to learn, but that's not the case once you cross that line. Okay, well, that's a synthetic experiment and with symmetric label noise. So then we looked at this more realistic data set called CIFAR-N and CIFAR-100N. Basically, someone took the the two CIFAR data sets, and they recruited a bunch of humans to assign labels. And kind of like ImageNet, they got at least 3 annotators for each image. And they came up with, they aggregated the human labels to get a noisy label in 5 different ways. That's these 5 categories, at least for CIFAR-N. And furthermore, they maintain a website, which is currently down for some reason, but they have a website, and they have like this leaderboard where you can, you know, report your results for your algorithm. And so we did that. I mean, we tried this out, and it works remarkably well. Like it, in 4 of the 5 ways of aggregating the human labels, this method is the best on CIFAR-N, and it's also the best by a large margin on CIFAR-100N. So, I mean, so that was a little bit surprising that A, that it worked that well, and B, that no one had done this before. But I guess the Dino feature extractor had only been out for about a half year at the time we tried it. And that turned out to be pretty important. So the takeaways from this empirical part is that this temporary overfitting, the degradation in performance when you have noisy labels, it seems like that can be attributed to for poor feature extraction. So when you train ResNet 50, you train all the weights with noisy labels, you learn poor features. If you have good features, the noisy labels actually don't hurt you, because our method, this noise ignorant ERM, actually works really well. Okay, and then after doing these experiments, we now have this stronger desire to understand why is self-supervised, why does self-supervised learning provide such robust features? You know, theoretically, is there a way to analyze that? Which, you know, several people have already worked on that problem, but I think it's a pretty poorly understood question. Let me just say very briefly, I focused on posterior drift, but this technique based on relative signal strength actually can be used to study domain adaptation in general. Domain adaptation without any assumptions relating source and target distribution, other than the relative signal strength is at least kappa with probability 1 minus epsilon. And you can get the same types of upper and lower bounds, and the conclusion that you draw in that case is not noise ignorance. It's that so that the optimal thing to do is assume that the type of domain adaptation is covariate shift. Even if it's an arbitrary type of domain adaptation, just assume that it's covariate shift, apply a covariate shift algorithm, that'll be optimal in this same kind of minimax sense that I've described here. Okay, so this slide is not, this is work in progress. So you could call it conjectural, but for everything else, we have a paper. All right, so in conclusion, relative signal strength is a pointwise measure of transferability from a noisy distribution to a clean one. Posterior drift is a good model for classification with label noise, a very general model. And our conclusion, both theoretically and practically, is that noise ignorance is, you know, performs well. Yeah, I mean, there's a phenomenon that's been observed in other distribution shift kind of problems, which is that ERM is hard to beat, right? So we observe that here. It's also been observed in a problem called domain generalization. So I don't know, it's somewhat a recurring theme. Okay, I'll stop here. Thank you for your attention.
Any questions? I'm not sure if there's audience question, but I mean, from the Zoom.
Yeah, nothing in the chat.
Any questions on the live audience? On slightly off topic, you mentioned you've done some previous work using a different risk measure for binary classification. What would you use besides the 0-1 loss? What was the other?
Yeah, so what other loss functions or performance measures are there for binary classification?
It's a freshman question, but I don't know.
I mean, there's actually a lot that people have looked at. And so one would be like a cost sensitive risk.
Oh, I see. So a weighted.
Yeah,
Okay.
yeah, that'd be like a simple answer.
Yeah. Okay.
You could have a name and Pearson criterion. You know,
Something like that.
minimize false negative probability subject to a constraint on false positive probability. You could look at, you know, maximize precision subject to a constraint on recall. That would be common in like information retrieval type settings. So to name a few.
Other questions?
That's one question. So can we go back to the accurate test accuracies with the theoretical bound figure? Yeah, just
Oh,
like 2 slides. Yeah.
Yeah.
How do you calculate the theoretical bound? Because I think the bound have the dimension V and the sample complexity N in that. So how do you
in this case, it's a little bit, it's something simpler. So this bound is true because of the fact that we're using symmetric label noise. So when you do corrupt a label, it transitions to each of the other labels with equal probability. And so because there's 10 classes, this line occurs at 0.9. That's actually another part of our paper that I didn't talk about, like why that line is right there. It's
So we can drop the second term, the big O term, because this kind of symmetric label noise, right?
Oh, yeah, so maybe how does the bound change if we have symmetric label noise? Yeah. If you have symmetric label noise, that is actually, as long as this noise rate is less than 0.9 in this case, you can actually, this irreducible term goes away. Because the clean and noisy based classifiers agree everywhere. So this is I pulled this from our paper, and it serves to demonstrate some things I didn't really talk about, as well as some things I did talk about. So maybe I'll rethink its inclusion, but
Thanks.
Yeah.
I mean, the question was just asked using the word bound. I don't remember if you used the word bound. I mean, it's maybe a bound, it's a lower bound to the right of the vertical line and well, an obvious upper bound to the left. I mean, I didn't hear it as a bound myself. I heard as well, you can't do anything to the right of this line. We're talking about the dashed red line here, right? Is it really a bound? Phase transition or something.
So this, in general, it's going to be 1 minus 1 over k, where k is the number of classes. That's going to be the threshold if you have symmetric label noise.
Yes.
That is the threshold below which the noisy and clean Bayes classifiers agree,
See.
and above which they don't. And that's also something we showed in our paper that had kind of been hinted at in prior work, but we kind of fully characterized it.
Other questions? So perhaps one question I might have is like, so in terms of the like algorithmic recipe or proposal, so the high level idea is that, let's say if you are fitting to the label noise, we want to avoid fitting with, in some sense, a high dimensional model. Because like when we are fitting ResNet 50, then it's kind of like perhaps a much larger model with like, I don't know, 500K parameters. Whereas with linear model, it is more low dimensional. So like it's kind of SSN, SSL plus linear is kind of combining the idea of, okay, let's, on the high dimensional side, let's do self-supervised, avoid the noise, and then linear is like kind of low dimensional.
Yeah, there's also just the idea that a linear classifier is going to be intrinsically robust because it's a simple model. So that could also partially explain. So the takeaway is you want robust features that are somehow robustly trained, you know, that are not going to be influenced by label noise. Because if you do this full training, like the ResNet 50, the yellow curve, you're gonna, the label noise will impact the extracted features. And it's gonna give you poor performance. So the key is you want features, you want a feature extractor that is not influenced by noisy labels. Noisy labels are bad for feature extraction. Once you've got that, then you can do something very simple. So
I think at some point I also saw a paper where like, I mean, somewhat similar, but like, I mean, not the noise setting, but for imbalance data, like this proposal of, okay, let's not worry about imbalance, but let's do self-supervision and then, you know, do linear probing, or rather than trying to develop a loss function or post-hoc calibration. Yeah, I mean, yeah. So indeed, I guess like this SSL idea is pretty good.
yes, one other thing you might think to try is take a foundation model and then fit a linear model on top of that through a classifier, and then do fine tuning of the whole thing. And a reviewer actually suggested that we try that, and so we did, and it actually worked worse. That degraded performance.
Did you do like low rank fine tuning or global fine tuning of the whole?
What did we do?
Oh, okay.
Global.
Yeah, that's a lot of free parameters to fine tune.
Yeah, it's a lot. Yeah, there's lots of ways you could do it. So that's true.
Global again, yeah, interesting. Maybe high versus low, or yeah.
Yeah, maybe low rank adaptation is a better approach, or I mean, if anyone has experience in that domain, you know, we'd be interested, but
I find it also interesting that like this SSL plus, you know, fine tuning idea, like even the language models are similar now, right? Because they're also like still like self-supervision plus instruction tuning. It's kind of like different words, but like still continuation of the same idea in some sense.
yeah.
Because what is instruction tuning? It is again kind of like supervision. But it comes at the end, basically. Cool. Oh, yeah.
I have a question. So this, what is it that has the property of immunity? Like, is it the model that's immune to the loss function?
Oh, pi, like, or maybe not pi. It's a set of distributions Like, it's like a type of domain adaptation, a class of domain adaptation problems. How do I want to say this? A type of domain adaptation problem is immune to a certain performance measure if being ignorant is optimal, basically. So
Is the model included in that performance measure? It seems like if
no,
the
no, it's just about the Bayes classifiers.
seems like if the number of features was larger than the number of samples you had, the linear model would still overfit, right?
Oh, yeah, what if, I mean, I don't know, we did regularized logistic regression, so maybe penalization would help. I don't know.
Is ResNet 50 kind of a state-of-the-art classifier here in the no label noise case?
I mean, I'm sure, probably not, right? There's, like
Because Dino plus linear is doing a lot better than that, right? Which is.
well, but you said no label noise
Yes,
case.
exactly.
Oh, right, Dino, well,
Right, I'm
but
curious
he-
how well the unsupervised
yeah,
linear does compared to state-of-the-art, without label noise.
I mean, it's basically a CNN, right? And people have gone beyond CNNs,
I see, fair, okay.
so
Yeah, okay.
I mean,
Slightly. I don't know how
slightly.
much.
depending on how carefully you set them up, I guess.
Dino plus linear is working remarkably well there, at least.
Yeah.
This graph.
Yeah,
I mean, in fact, basically, one can even try like just do diner and then no label at all, and see if the clustering gets it. Right?
Oh,
Total
interesting.
unsupervised after permutation. Yeah.
yeah, maybe they're so well, the classes are so well separated. That'd be interesting, like how much of this is due to just Dino just creating these super tight clusters? I mean,
I feel, I don't noisy label, I feel a similar curve like the yellow one.
what if we just do Dino and we feed in CIFAR images and we run k-means
Exactly.
with 10, k equals 10. Does that, do those clusters, how accurate are those clusters? Yeah.
Fine, yes, thanks.
Foundation.
Oh, sorry, someone has this.
Classification task, right? What I do is most of the